Great. Also, so first of all, some thanks to Emma and to Ignacio for organizing this. It's been really nice to visit you and see so many people here. Also want to thank my colleagues in the Osmosis project. Osmosis stands for, it's a terrible acronym, by the way. It's Ocean Surface Mixing, Ocean Submesoscale Interaction Study. And basically, it's a bad acronym because there are two parts of the project. One is looking at Langmuir turbulence and the effect of surface waves on mixing processes, and the other is looking at what happens at fronts in the mixed layer. So the ocean surface mixing is what's looking at the Langmuir turbulence and waves, and the part that I'm more working on is what's happening when you've got a horizontal density or buoyancy gradient in the mixed layer of the ocean. So I'm going to talk about intense upwelling in anti-cyclonic eddies. So here's the plan for today. I'm assuming that people here aren't really familiar with what's been happening in terms of submesoscale dynamics. So a lot of the talk will just be establishing the basic concepts and the important dynamical processes. And then in the second half of the talk, I'll be looking more at the numerical modeling that have been done and the results that have come out of it. And then in a curious inversion of the normal way, we'll be coming towards the end with some more motivation towards the end of the talk before concluding. So the first question is, what we're looking at today is submesoscale. So we're generally familiar with the mesoscale. This is the big eddies. So submesoscale is obviously things that are a bit smaller than the mesoscale. Some of the people who've done a lot of work on this are John Taylor at Cambridge and Raf Ferrari at MIT. So this gives you a sense of what we're talking about. This is the top image is sea surface temperature. Obviously, this is the North Atlantic. And we see that we've got a general equator to pole temperature gradient. But that gradient isn't evenly distributed. In some places, such as up here near the edge of the Gulf Stream, we find that we get a very rapid temperature change. So we've got lateral density gradients. And in the lower box here, we zoom in on this area. And here we can see some of the different scales that are at work. For example, over here, we have a mesoscale eddy. And the bar here indicates that this is a scale of about 100 kilometers. But we also see that we've got structure down here on scales closer to 1 or 10 kilometers. And this is the submesoscale. Now, a lot of the work, there's been great work done on this, especially over the last 15 years. And it's focused really on places like this, like the Gulf Stream, places where you get these really strong horizontal density gradients. But the one question is, what about in this area here? Is there also submesoscale processes happening here? And I guess for this audience here is also out here in the Mediterranean, where we may not have a particularly strong current, but are we still getting the kind of processes that have been studied at these big ocean fronts happening out in the open ocean away from boundaries? So next question is, why do we care about the submesoscale? So here's back from the same paper from Taylor and Ferrari. And this is, again, the sea surface temperature image. And then this is some chlorophyll concentration. So obviously, this is really ocean color. And they use some kind of model to then estimate what the chlorophyll concentration is. And we see that on these small scales here, this is on the chlorophyll concentration is in milligrams per meter cubed, that we're getting changes on the order of 2 or 3 orders of magnitude happening over distances of 1 to 10 kilometers. So this is one reason we're very interested in the submesoscale. It seems to be areas where the constraint on the large-scale circulation, that it's hard to move fluid up and down, is broken. That on the small scale, you're not so constrained by the planetary rotation, and that you can really get stronger vertical velocities, and so then get stronger biogeochemical responses. There are other interesting aspects. For example, on the large scale, the theory for that is based on quasi-geostrophy. And quasi-geostrophy implies that energy, when it's put at a certain scale, generally goes to larger scale. So you end up with big eddies. But the problem is that it's hard to actually dissipate the kinetic energy. So it's a big issue in oceanography. You've got most of the energy is in these big mesoscale eddies. But to dissipate it, you've got to get down to this millimeter type length scale to actually generate the turbulence to dissipate it and turn it into heat. So how do you break this constraint of the large scale circulation and get turbulence generated right down to these very small scales? And it's thought that as well as bottom friction, obviously, and boundary friction is one place where this can happen. But another area is at these smaller length scales, at the submesoscale, that here also you can break this constraint that you're very constrained by the planetary rotation and start getting energy down to smaller scales. So to understand what we're talking about today, the key concept is really everything's going to be thought about in terms of potential vorticity. So you may or may not work in potential vorticity. So we'll give a reminder of how it works and what the important parts of it are. This is the basic formula for it. So it's going to be denoted by Q, and it's equal to the planetary vorticity plus the curl of the velocity field, and that's times the gradient of buoyancy. So buoyancy is then like the negative of the density gradient. Now, this is just basically a sense of the way in which the flow is rotating, and it's taking into account the slope of the density surfaces and whether you've got lots of stratification or less stratification. So obviously, nobody wants to get out of bed in the morning and start having to think about this formula because it's just too complicated. So as oceanographers, what we always try to do is to simplify this. So the first simplification is to do this. Let's say Q is just equal to F, which is the planetary, the Coriolis frequency, times n squared, where n squared is the stratification. So to give you a sense of what we're talking about, here's some of the model output that we'll be looking at in more detail later. And in this model output, the colors measure the potential vorticity, and then the black lines are temperature or buoyancy surfaces. So I've chosen this section because here we have these downward doming isopycnals, or buoyancy surfaces. So we see that we have an anticyclone here, and that's what we're going to be most interested in. So we see that in the, it hasn't come out well actually. So in the anticyclone, we have very large positive potential vorticity here. We've got a generally mixed layer with low potential vorticity. And then in the anticyclone, we've got some PV, or potential vorticity, or PV, over here. But at this area here, it hasn't actually come out very well. It's actually blue. You get negative potential vorticity. And I'll come back in a minute to talk about why negative potential vorticity is very important. But the first thing we want to do is understand how we could actually arrive at a state of negative potential vorticity. So the first approximation is to say Q is equal to F times n squared, and that's what we show here. So what we see is that down here in the thermocline, where the potential vorticity is dominated by the stratification, if you compare the two plots, we do a pretty good job at describing this. Then here at deeper depths, we actually have too much potential vorticity, so we're not doing quite such a good job here. We do pretty well up here in this side of the anticyclone, but here with Fn squared, we end up with positive PV, whereas in fact we have negative PV. So we're missing something. We need to make this a little bit more complicated, unfortunately. So the next step is always to say, okay, so now potential vorticity is equal to F plus the relative vorticity, the vertical component of relative vorticity, multiplied by stratification. So now we see that down here, if you look at this little dot, for example, this is represented much better. So down the thermocline, we're now doing a pretty good job of estimating the PV with this formula. However, we still end up with positive potential vorticity here, whereas we have negative potential vorticity up here in the mixed layer. So we can see why that might be, that over here, the black lines are all stacked on top of each other. So we've got lots of n squared, lots of stratification. However, in this area of interest, the slopes are actually close to the vertical. Of course, the aspect ratio of this plot is 200 meters this way, 200 kilometers this way. These things aren't really vertical. They're more like a very shallow slope of maybe 3 degrees to the horizontal. But nonetheless, here we've got we definitely have a horizontal gradient as well as just a vertical gradient. So in this situation, what we've learned to do at these open ocean fronts is then start to take this horizontal gradient into account when estimating the potential vorticity. So this again is the full formula, but now we can go another step of complexity and say, okay, we've F plus the relative vorticity times stratification, and now we'll take this horizontal gradient in buoyancy into account. And so we do that by taking the vertical component of this. So this is dV dz, the vertical shear of the flow, multiplied by the horizontal buoyancy gradient. You may not have a sense of what this looks like, so let's just look at this term on its own for a second. So again, here's the full PV from the same shot, and this is what dV dx times, or dV dz times dV dx is with the minus sign. And we see that this term is negative. So this is what's setting the negative PV that we're getting up here in the mixed layer of this anticyclone. So it's negative here, and there's a small positive area here. Now the important thing is that it's not just a coincidence or some curious alignment of the flow that this is negative. This is actually a fundamental reason why it's negative. And this comes back to just the basic thermal-wind relation that you learn about when you start oceanography. So thermal wind just says that you have a flow that's in geostrophic balance. So you have FV is equal to the pressure gradient, and you're in hydrostatic balance. Then you differentiate this vertically, this horizontally, remove the pressure, And what you end up with is F times dV dz is equal to the horizontal buoyancy gradient. So now the term we're interested in has both dV dz and dV dx. So we can use this. So we have the formula is minus dV dz times dV dx. So we can use this to eliminate dV dz. And instead the formula is minus 1 over F times dV dx squared. Now this is really important if you're using gliders. And this has been really useful using gliders because now you can estimate dV dx from your glider profiles if you're doing lots of stations together. And you can also estimate the stratification from the gliders. So it gives you a way of actually making a really good estimate of the potential vorticity just from glider data without needing ADCPs or altimetry or anything else. And so we see that because this term here is squared and we have a minus sign, this term here is systematically negative. So it's systematically reducing the potential vorticity. So in the mixed layer, where the stratification is relatively small, that the negative contribution from this term can be enough to actually mean you go from a state of positive potential vorticity into a state of negative potential vorticity. And we'll see why that's important here. It's not always the case. Up here, it's a little bit different. That's because dV dz also includes a contribution from the Ekman shear, because there's wind forcing in this model. But here, it's more due just to the fact you've got thermal wind, and that's what's driving the vertical shear of the velocity. So that's how you get negative PV, but now we haven't really established why we're actually so interested in this negative PV. So we'll go back to basics on this. So here are 3 buoyancy surfaces. They're going from sort of cold here to warm here. One of the nice things about thinking in terms of buoyancy is that it scales in the same way as temperature. So more buoyant is warmer. So I think it's a little bit more intuitive than having to remember to turn around density. And so we think if we have a particle here, we have an ocean just at rest, just with stratification, and we take that particle and we give it a little bump upwards, then what happens? Well, we find that when the particle moves up here, it's not as buoyant as its surrounding, so it gets pushed back down towards where it started from. When it reaches its starting location, it's back where it started, but now it has momentum, so it overshoots, and now it's too buoyant and comes back up again. And of course, this is just the most simple gravity wave you can imagine. Now the next step is to think we have the same situation, but now we've got no flow, but we've got our vorticity vector here, zeta, is just based on the planetary vorticity. So this vorticity vector pointing upwards. Now what happens if we take this particle and we push it sideways? Well, it goes sideways, and then it's accelerated by the Coriolis acceleration in the northern hemisphere to the right, and it starts going around in a circle. And of course, this is just an inertial oscillation. So this is just what's happening because of this vorticity. So you can think of this in the same way that we've got buoyancy surfaces, that we're moving the particle away from where it started, and it's coming back around to where it started in the first place. Now, meteorologists thought of a nice way of thinking about this in the 60s, and that's in the same way that we have buoyancy surfaces, we can think of momentum surfaces. And they have an orientation, so this one here is M, then there's a larger momentum surface and a smaller momentum surface. So in the same way that a particle here, sort of, when you knock it upwards, it's pushed back towards its original surface. You can think of it in the same way a particle pushed here is then pushed back around its original momentum surface. And that's what the vorticity vector wants to do. It wants to return a particle back to its original surface. And of course, if you have a particle and you do it some sideways, then you get some combination of the two, and it's an inertial gravity wave, just as we're all used to. However, we saw just with the model output that we weren't in a situation where the buoyancy surfaces were flat like this. Instead, there was a bit of a slope to them. So we think about this scenario here. So first of all, we still have stable stratification. So it's still warmer above colder. So there's no problem with convection or anything. But now we've got something of a slope here. And now in this situation, that jumped a bit more nicely. In this situation, the momentum surfaces also change because they're based on the vorticity, and the vorticity is no longer 0, 0, F. Because we have a horizontal buoyancy gradient, we now have thermal wind shear, and the vorticity vector is now pointing off to the side. So now this is the angle. So the point is now here, these momentum surfaces are steep, and the buoyancy surfaces are shallow. But that's changed around in this new situation Now the momentum surfaces are steep and the buoyancy surfaces are shallow. So we think about what this means. Now if we have a particle here, and let's imagine we push it along its buoyancy surface. So this is easy. We're not fighting against gravity. We can just do this quite easily. But as we do that, now this particle has left its original momentum surface. So the vorticity kicks in and accelerates it this way. As soon as that happens, it's left its buoyancy surface. So now it wants to go back upwards. So now in contrast to the previous situation, where if you moved the particle away, it was pushed back towards the starting point. In this situation, we move the particle this way, and instead it's accelerated away from its original starting point. And of course, this is just the definition of an instability. In this case, this is called symmetric instability. And it's interesting that if you read the specialized literature on symmetric instability, it's often quite complicated. And this simple idea that is at the core of it is often quite buried deep, and you can read for months without actually seeing that it's a relatively simple process that's happening here. That the two forces that normally bring a particle back towards its original location, when this situation here, which corresponds to negative potential vorticity, in this state, that any little perturbation to a particle will result in it accelerating away rather than just coming back to its original location. And that's the basis of what we're looking at, that once you get an area with symmetric instability, any particle will just shoot off, and so the ocean is very unstable in this situation. So there is a movie I'm going to try to show you. No, it's on the wrong thing. Okay, I'll skip that. I had an emergency last night in Ibiza that the whole thing collapsed. So we'll come back to how negative PV is generated, because we saw we had it in the model, and normally potential vorticity is a very conserved property. So in order for the potential vorticity to become negative, either we need to have some kind of frictional process, such as wind at the surface, or else we need some heating or cooling, or generally cooling at the surface, to be applied to actually give you negative PV. So this is a more simple model simulation that I've run, and it's just a warm filament surrounded by two cold areas. It's periodic this way, so something can come out here, come back here. It's only 50 meters deep, so it's as if you just got two fronts in the mixed layer. And now normally, if there was no wind, when you start this, you would expect that the warm water starts flowing out over the top on both sides, and the cold water flows down underneath until it arrives at a state of geostrophic balance. However, with the wind going into the board, we have an Ekman transport going that way across the domain. And we see what that means. So it's going to run for about sort of 24 hours. So first of all, this water is lighter, so it starts overrunning. But now the wind kicks in and starts transporting this colder water over the heavier water. Now that normally leads to convection. In this model, the convection is parameterized. But you see what it means on this side, you end up with weak stratification, but strong horizontal gradients. So this is the same situation we had before. Weak stratification, but still with horizontal differences in temperature. And this is the situation that gives you negative potential vorticity. On a front where it's the opposite way, then you see that the wind helps the restratification. So this is the important point, that here, this is what's known in the literature as a down front wind. The idea is that in this situation, the wind is going in the same direction as the surface current. And so when that alignment happens, you push cold water over heavy water, it convects, mixes, and you end up with negative PV after a few hours. Okay, so based on that, let's have a look at some of the numerical modeling. The idea is that we're out in the open ocean in the Atlantic. So we set up our model like this. It's got a stratification, so it's about 4,000 meters deep. It's 256 kilometers on either side. And the idea is that we run it with grid spacing of 4 kilometer, 2 kilometer, 1 kilometer, and half a kilometer. And the idea is that at 4 kilometer, we're resolving the mesoscale well. And as we go to half a kilometer, we start resolving the submesoscale. And we want to see how it changes as we go through that change in resolution. It's doubly periodic. So anything that goes out this side is back in here, anything that goes out here is back in here. The idea is we're out, say, in the middle of the ocean, there's not many boundaries near, so we don't want to think about boundary processes, we just want to think about eddies interacting with each other. And then it's stratified. So we got 200 levels in the vertical. So in the mixed layer, we have 3 meter resolution. So we're getting good, decent resolution there, and it's on an F plane with no planetary beta effect. So we give it some wind forcing. We start off with stratification, but we have no horizontal gradient, and so nothing can happen. So what we do is we generate an artificial stream function for the wind that looks like this. So at the start, this area here, this is maybe about 50 kilometers across. There'll be a bit of Ekman convergence. So the isocyclones get pushed down. Here it's the opposite. So water gets pulled up. So the flow comes into geostrophic balance. And then after just 2 or 3 months, then you start getting a turbulent eddy field emerging, as you'll see in a minute. And then we also add, as well as this weak wind with spatial structure, we also add a wind that's going zonally. And so that means that there's an Ekman transport always going from the top to the bottom, as I'll show you again later. What we do is then we force this with a monthly climatology of heat forcing, so that the mixed layer is 10 meters deep in summer and then 200 meters deep in winter. So we can see how the behavior of the model changes as the mixed layer changes. And that's the work that's in another paper, which is on the seasonal cycle of the mesoscale flows, which is in the final stage of review at Ocean Modeling, if you're interested in that. So I'm going to show you what the model output looks like. This is going to be over 180 days of winter from the 5th year. The field is surface relative vorticity, normalized by F. So the values here are quite strong. It's going from +2 to -2. And what we're going to notice here is that we've got 2 features. This blue area here is negative relative vorticity. So it's an anticyclone. And then it's in a dipole with this cyclone. It doesn't actually matter whether the 2 eddies are next to each other or not, that we see the same behavior in both cases. But as we go through winter, if you keep an eye on what happens in the anticyclone versus what happens in the cyclone. But notice first that at this point at the start of winter, when the mixed layer is shallow, they're both relatively homogeneous. If you go around some circle in the eddy, that everything's just the same on that circle in both eddies. So now we're running at 3-day jumps. So nothing happens here yet. The eddies are just being evected around this turbulent domain. But now if you watch the anticyclone from this point, you start to see submesoscale filaments are generated inside the anticyclone. Whereas if you look at the cyclone, you see that everything remains homogeneous inside the cyclone, but something's happening inside the anticyclone that generates the wrong sign of relative vorticity. So a lot happens there. So to slow it down a bit, here's just a snapshot of what it looks like in late winter. So here's the cyclone, just in a zoomed in area. Temperature, so it's cold at the center. And if you go in any line outwards, you find that it just gets warmer as you go out. So it's relatively simple. However, in the anticyclone, you can see you got warm temperatures here, and they're going around here, and you have cold water intrusions. And if you go out in any line, you find it gets warmer, a little bit colder, a little bit warmer, a little bit colder. So here, what you have is just solid body rotation, whereas here, you have strain happening inside the mixed layer of this anticyclone. Then here we have the relative vorticity picture we just saw. So we can see we've got lots of little filaments here in the anticyclone. Now the key point is this has been seen a few times, but the new part here is that we're looking at it in terms of potential vorticity. Now these 3 fields are at the surface. This is the potential vorticity towards the base of the mixed layer. Here again is the cyclone. There's just nothing happening there. You're in the mixed layer, PV is low, nothing going on. Over here in the anticyclone, we see lots of positive large values of potential vorticity in the mixed layer. Now we're cooling at the surface. There should just be 0 potential vorticity here, but we're seeing lots of positive potential vorticity happening. And if we look closely, for example, say at this point here, we have this filament, and then here we have this filament. So we see that whatever is generating this process is just reflecting the fact that we have large positive potential vorticity values in the mixed layer of this anticyclone. Now, if you look on vertical lines through these eddies, you can get a better sense of what's going on. So here's the cyclone. Again, the black lines are temperature surfaces. So it's doming upwards, as we expect from a cyclone. And then we've got not much stratification here at the surface because we're just cooling. However, in the anticyclone, we see something quite different. First of all, again, we see the downward doming isocyclones, as we would expect. However, here, what should be the mixed layer, instead, we have lots of these positive potential vorticity values coming up into the surface. So this suggests that in the anticyclone, we have exchange between the thermocline, where we have positive PV, and we're getting this water coming up more or less along isopycnals into the mixed layer. There is an asymmetry here between this side of the anticyclone. There's not much stratification here at the surface. And here on this side of the anticyclone, we get some near-surface stratification. So we can account for that. So one issue with the runs I've shown you before is you can see there's a whole lot of stuff going on at once. It's very turbulent. It's hard to follow an individual feature. So now what we can do is take the run at 4 kilometer resolution and interpolate it to the half a kilometer grid. Because in 4 kilometer, it looks like this. You have a cyclone here at this point, and you can see at 4 kilometer, the cyclone is just a circle with no filaments. And here's an anticyclone, a warm area, and again, no filaments. And what we're going to find is that within 3, 4, 5 days of going to the higher resolution, we're going to get this filamentation emerging very quickly. So the boundary condition is simpler for these. So we have this complicated wind structure for the other runs. In these runs, the wind is just zonal. So it's just wind going to eastwards, a weak wind corresponding to maybe 6, 7 meters a second. And so the Ekman transport's going from north to south. Here's the potential vorticity near the surface. So in the cyclone, the wind is going to the right. So we got warmer water in the north and colder water in the center. So what that does is push the warmer water over the colder water, and that generates stratification. So that was like the right-hand front in the two-dimensional model we saw a few minutes ago. And so there we get positive potential vorticity. In this area here, we get the colder water from the center being pushed over the slightly warmer water outside. So here we're pushing cold water or heavy water over light water. So this is where we get zero stratification and negative potential vorticity. And that's what we find. Then here in the anticyclone, the directions are reversed. Here we have, in this region, the colder water being pushed over the warm water in the north. And then we get negative potential vorticity here in this part of the anticyclone and positive potential vorticity down in this part of the anticyclone. So now we're going to run this at 250 meter resolution. And this is the potential vorticity from this run that's taken, this is the 4 kilometer run interpolated to 250 meters. The red color, the mixed layer of an anticyclone is like a fruit bowl. It's just like this. And we're taking a slice across the bottom. So these values here are in the mixed layer, and these dark red values are in the thermocline. And this is just a little bump in the base of the mixed layer. However, you'll see now what happens. As we start, we've got areas of negative PV throughout this kind of area here. And then what we start seeing growing are these filaments here of positive relative vorticity. Now you should keep in your mind, wherever you see red areas, this is thermocline water that is now being sucked up into the mixed layer. And so we see that these are very submesoscale filaments. They're maybe 1, 2, 3 kilometers wide, and they're being generated and pulled up throughout the interior of this anticyclone. There's been a lot of work done in terms of the submesoscale dynamics, and normally they focus, say, on the edge, the area here at the edge of the eddy. So the big difference here is that we're showing that these submesoscale instabilities can happen throughout the eddy. So you're really having this intense upwelling happening over a much larger area, not just the little area on the edge, but the entire area of the eddy. So this is then looking this on a vertical section. I think this might give you a better impression. This area here is on the right. So this area here is what's called the downfront area, where the wind has pushed cold water over warm water. So you have negative potential vorticity and no stratification. And here is the opposite area. Here you've pushed warm water over cold water. So you have a little layer of stratification here. And then down here, you still have negative PV, because this water here comes around the eddy and goes back in this side. And now we see what happens here. Again, it's going to take a couple of days. The instability needs a chance to grow. But this area here and this area here are, again, should be highly unstable to this kind of instability. This is the bump in the mixed layer that we could see in the previous run. So first of all, over here, so from this point, we start seeing little sort of things start to grow. And we notice that it's along the isopycnal surfaces. and we're getting strong growth like this, note that the distance here is 40, 50 meters, and these things are happening relatively quickly. So we're having vertical velocities of 50 meters, 100 meters a day. Now over here, it really gets going, so you start to see wherever you get strong blue values, then you'll start getting strong red values. So this process, what happens is that you get this negative PV, so you get this symmetric instability growing, and it keeps on growing until it gets into an area of positive PV, and then has to absorb that positive PV water in, mix it through, and that's what restores stability. So when you get an area of negative PV, it's not just the instability happens there in the mixed layer, but it has to extend into the thermocline and suck up thermocline water into the mixed layer in order for everything to settle down. And you see you get a very, very messy process, but you get continual upwelling of thermocline water into the mixed layer. So just to stop that for a second, this is what it looks like. Here we see, for example, here 3 filaments developing in the region of negative PV, and this is the vertical velocity. And you see that the vertical velocities here are aligned along the isopycnals, and they're of order 50 meters a day. At times we see 100 meters a day or even 200 meters a day. And then we see more of them developing over here. So one question then is, okay, we're getting this at 500 meter resolution, but how much resolution do we actually need to start seeing this process? Because people have run models of the, say, the North Atlantic or the global ocean, and they find that they don't get enough primary productivity. So you have to understand what resolution you need to run your model at in order to get this kind of upwelling. So here we go from 4 kilometers, and we see that it doesn't show well here, but we have negative potential vorticity, but no filaments. And then from 2 kilometer and 1 kilometer, we're starting to get a bit of it. And really with a half a kilometer and 250 meters, we're really starting to get a lot more. Now, one thing to notice is that these filaments continue to become sharper and sharper as the resolution is made finer. So that means that we haven't actually arrived at the point of what we call convergence. So if I go to 150 meters or 100 meters, it looks like they're going to continue getting a little bit sharper, and at some point they'll stabilize and stop, but we can still go to higher resolution to actually resolve this. But at these, already at 500 meter, 250 meter resolution, you should be getting this kind of upwelling happening. And that gives you a sense that this is happening on a scale of 1 to 3 kilometers. So, more motivation. That's the kind of dynamical process that we saw in the model and we're interested in. Now, the exciting part was we had a look at the literature, and then we found that there's a lot of papers like this. This is from Hansen et al., and it looks at anti-cyclones in the Norwegian Sea. And here we see it's from ocean color data that they see, for one thing, the purple color shows not much productivity in the area around the eddy. So we must be somewhere in an oligotrophic region. But inside the eddy, we're getting high productivity. And we see it's got this submesoscale structure. It's happening on small scales, and then you're getting much more intense productivity. So this suggests that something is happening inside this eddy, which is then sucking up high nutrient water from the thermocline that's driving productivity. Or there's my favorite picture, which is this one from off the coast of Japan. So this one is a false color sea whiffs image. So again, we see outside the eddy that this is in bloom conditions. There's some bathymetry, there's some stuff happening, but here there's not much happening. And then inside this anticyclone, we can clearly see that there's a lot of primary productivity, and it's happening based in these small scale, submesoscale filaments. So this ties into a larger question. People are trying to estimate the carbon budget in the ocean, and for 30 years, people have estimated the amount of primary productivity that happens by looking at oxygen measurements. Now, you've probably guessed I'm not really a biogeochemist, I'm more a physicist. But then what people have found for a long time is that they're seeing a lot of productivity from the oxygen measurements, but when they try to estimate the amount of nutrients that are happening to supply that productivity, they come up short. So one idea has been that there's lots of activity happening in eddies that then we're missing, and so that's what's explaining the missing nutrient supply to the mixed layer to drive this productivity. And so various theories have emerged. I think the main one is probably an idea that you get Ekman pumping within eddies, and that's been looked at by Dennis McGillicuddy and people in Woods Hole. But the upwelling associated with that is more like 10 centimeters a day. So to give you a sense, we're looking at a process which is upwelling velocities of 100 times a lot of the processes that have been happening already. So to test this, we've taken the same model and run it with a biogeochemical package, a very simple experiment, and I'll apologize to any biogeochemists. Oh, sorry, this hasn't shown up well. So we run it at a few resolutions. So we're cooling at the surface. So what we do is we make sure we're missing one nutrient in the mixed layer, and then we give below the mixed layer, we give that nutrient the same distribution as potential vorticity. So basically it's in the thermocline, but it's not in the mixed layer. And then we run the model. So when we run the model, we see first of all, there's some areas here where we get some productivity straight away. These are just areas where the mixed layer was deep enough to actually catch the nutrient, so then it just gets diffused up to the surface immediately. So that's not really very interesting. The more interesting area is down here. So down here we see the anticyclone, and we see that at 4 kilometer resolution, maybe we get a little bit of productivity, but at 250 meters resolution, we get lots of productivity happening in this anticyclone. So we're getting something that's able to absorb this nutrient from the thermocline and bring it up to the surface quickly and get lots of activity. We can look at that as a movie. So this is the 250 meter run. This is biological productivity at the surface. And we started running here. So first of all, we get these areas here that aren't very interesting because it's just the mix there is deep enough to take our nutrient right up to the surface. But the anticyclone is down in this region here, and that's what we're most interested in. There's also a cyclone up here where just nothing happens because this dynamics doesn't happen in cyclones. So it takes a few days because we've put it a bit below the mixed layer to make sure we don't cheat. And now from this point, we start seeing some upwelling happening. And first it's concentrated in these filaments, but then it gets kind of spread around throughout the eddy. And it just continues to grow throughout the whole thing. And because this is continually upwelling, this is something that then can sustain a productivity bloom for quite a sustained period of time. So in the Atlantic, for example, they see agulhas rings that come from South Africa across the Atlantic, and the anticyclones have blooms that last for 2 or 3 months, indicating there's a process there which can continually resupply nutrients back into the mixed layer. So this is at the surface. If we also look at this, compare this, this hasn't come out well. This is at the surface compared to at the base of the mixed layer. So the base of the mixed layer, we can see that this is really concentrated in filaments. And then as the mixing gets larger, it gets spread out throughout the eddy. But essentially, the productivity is starting from this filamentary upwelling and is then being spread out and diffused through the eddy. Okay, so the conclusions are that in these simulations, we're finding intense upwelling in submesoscale upwelling in anticyclones. The upwelling occurs in regions of negative PV and it's happening along isopic nodes. These are definitely the characteristics of symmetric instability. And this upwelling can supply limiting nutrients to the surface and so generate high productivity inside the anticyclone. Okay, so thanks for your time. Any questions?
Thanks very much for such an interesting presentation. Any questions from the audience?
What happens if you stop the wind?
If you stop the wind, it's all dependent on the wind. So this can only happen where the wind is extracting PV. So there will be some negative PV there left, but you'll then absorb some more positive PV fluid, and that'll mix, and then it'll be gone within a day. But generally, the point is that the wind here is relatively weak, just 5 or 6 meters a second. So it's a sort of wind that generally you would get a lot of the time. So you don't need a big storm to sustain this. Just a general cooling. If you have wind that's not stopped for more than a day, then you should get this continual process happening. And once you have the nutrients, then they're spread around, so maybe they should last for a couple of days.
You had a question, I guess?
You have shown that when you increase resolution, you get more and more filaments, but also they get thinner and thinner and thinner. So do you have any estimation of what is the net amount of water? So you have mentioned the velocity, vertical velocity. Is this the maximum velocity somewhere, or is the average velocity of those filaments? Just to compare with other more standard mechanisms of upwelling in anticyclones.
Yeah, so what I showed there with the cells of maybe 50 meters a day, that was a snapshot. So that's what's happening. But generally, that's a very typical idea of the vertical velocities. That it won't be the entire eddy, but a lot of the eddy will be subject to vertical velocities of 50 meters, 100 meters a day throughout areas. So that's not essentially that's happening every time we look at it. So it's a good sense of what the average would be. But this is one thing I need to do, is start to do the fluxes, but I wasn't sure if this I want to get some input from biogeochemists if the experimental setup is valid for actually estimating these kind of fluxes. So at the moment we're just concentrating on the fact that this mechanism exists and may have this application. And so some of my colleagues in Southampton, I'm talking to them about possible ways of improving thinking about the biogeochemistry of this.
Emma?
Thank you. When we saw the negative potential vorticity filaments coming down and then mixing up from below the mixed layer, how long were those filaments sort of lasting in the model? I just wondered.
The negative PV filaments. Well, generally the growth rate for symmetric instability is the order of hours.
Right.
So once you get it, so the issue, it took a while in the model because it's not enough to have negative PV. You then need a perturbation to actually get the instability going. So in the model that you have less perturbations than you do in the real ocean, because here we don't have tides, we don't have topography. So the internal wave field is relatively weak in the model. So they maybe last a little bit longer than they do in the real ocean, or the instability would grow faster. But generally a time scale of, they last for 2 or 3 days and then they're mixed away as that.
Yeah. Okay. Brilliant.
Just one question on one curiosity. Which kind of model do you use? The model, numerical model.
So yeah, I may have forgot to say that. It's MIT GCM run in hydrostatic mode. So it's not particularly, it's a pretty standard.
And the curiosity is the potential vorticity fields that you show looks like a finite size Lyapunov exponent pattern. So do you think there is any connection with these two quantities?
So you mean with the spiral pattern? So I think the spiral pattern is just that the instability happens like this and then it gets dragged around the eddy. So I think people have seen this kind of structure of the spirals and looked at it from finite time Lyapunov exponents. But I think that what the results here, because you're looking at it from the fundamental PV perspective, shows that you're getting an instability and then you're just dragging stuff around the model. So actually the Lyapunov exponent isn't the correct approach because you won't get to the fundamental cause of it. You'll just see the symptom rather than the cause. And it doesn't explain. So people have looked at, I think some guys, Lehan based in Tel Aviv, they've looked at it from this more dynamical system perspective. But the issue is that they say you then don't have a source of high nutrient water. So the idea with this is that because you implicitly have to take fluid from the thermocline to equilibrate the instability, that's the key part, that's giving you a source of high PV fluid that can then generate the other structures.
Any more questions? No? Okay, so thanks very much, Liam.
Right, thanks. Yeah, so the idea was we were running a model to look at seasonal cycle, and then over the last few months we saw this phenomenon. So people have seen this before, but never really looked at it with potential vorticity, and then you see lots of vertical velocity, but you don't really know what to do with it.
Excuse me, I am the director of the institute, and I would like to welcome you and thank you for this nice
thank you.
conference. I am a biologist, so I didn't understand very much, but at least it was interesting to see and thinking the biological implications of that.
Excellent,
so
thank you.
Welcome.
Thank you.
Thank you.
Okay, so things that we need is to take this back. Can I just unplug it?
Yep. So the white bit belongs to